So, I'm sorry, I need to just record that. So, basically we're going to use this idea that the simple harmonic motion and the circular motion are linked. The horizontal component of the circular motion gives me all the math I need for the simple harmonic motion. So let's imagine that we moved our mass to the right-hand side and let it go when the clock said t equals 0. And what we find then is that after a certain time, my mass has come round to here, and there's my displacement or my x component position, or whatever you want to call it. And I say, oh, hold on. The hypotenuse is just the amplitude, and the angle is omega, which is the angular frequency. It's like hertz, but it's in radians per second. The angular frequency times the time. And that will depend upon the spring, etc., etc. So I can say, well, from trig, x is equal to a cosine omega t, just from trig, just from components. Well, that's interesting. It only works provided I started off at this right-hand side when t equals 0. That's a little trick that's not necessarily obvious, but we had to do that to get this math to work. What we then do is we say, well, hold on, let's push this a little bit. So if the simple harmonic motion is the horizontal or the x component of my circular motion, then I have a tangential velocity, vt. So maybe if I take the horizontal component of that tangential velocity, I will get my velocity of my simple harmonic motion. How do I do that? I say, well, v is equal to, let's look at our triangle. We're using the big triangle now. And what we've got to realize is that if this is omega t down here, that is omega t there, which means that's omega t there. Now, what I'm interested in, which is the v, is opposite the angle. So this would be, vt sine omega t. It's the sine because now it's the opposite to the angle that I know. Why is it a negative sign? Because if you look at this, we've got a negative direction for my velocity. So I have a negative sign in there. This terminology is a little bit complicated. If you remember that, how did it go? It said that, if I remember my definition, SR theta, we said that theta is equal to S over R. That was the definition of a radian. And then I said, well, then, and what I learned was S is equal to theta R. It's angular. The linear bit, which is the chord around the edge, is equal to the angular bit, the theta, times the radius. So by analogy, I can say V is equal to omega R, and A, angular acceleration, is equal, A is equal to alpha R. So I learned this pattern. So for my velocity, I can say, my tangential velocity is equal to my angular velocity times my radius. And I know that my radius, of course, is my amplitude. So I get this expression, which is V is equal to minus A omega sine omega t by substitution. And then if I say, okay, well, now let's have a look. We've got a centripetal acceleration here. Let's take the horizontal component of my centripetal acceleration, and I find A is equal to minus AC cosine omega t. And here I know that my A is equal to alpha R, my AC, which is equals V squared over R, which equals omega squared R. Omega squared R. Let's substitute that in. R is A. I end up with minus A omega squared cosine omega t. So I'm getting this with a little bit of remembering about definition of angular to linear conversions, and then based on that also a definition of my centripetal acceleration. I have these things which you might not remember off the top of your head, but you've seen before and you can resurrect. It's like you might not remember it, but it's not magic. You've seen it before. And we end up with this expression, this family of expressions. For those who are just like comfortable with calculus, they can go, oh, well, look, I know this. If I have this expression and I differentiate it with respect to time, I get that expression. And if I differentiate that with respect to time, I get that expression. So some people just say, just give me the first line and I'll give you the rest, because I'm comfortable with the math of calculus. And others say, well, I'm never that comfortable with that. I know how to do it, but what does it really mean? This is doing it from fundamental physics. And it's illustrative, actually, that you can make an awful lot of headway on general physics. You can figure a lot out by simply combining equations, because if one equation is right and the other equation is right, you put them together, you've invented a new equation that's right, which is the new relationship. So I love this. I love this because, first of all, I'm a visual thinker, and secondly, because it's just out of, basic algebra and a bit of trig, we can figure out something which is incredibly insightful. I mean, this is golden. This is like, you could look at this all day and not figure out how to get those instantaneous values, and yet here they are. I don't bother remembering this because I can figure it out. Maybe I should remember it, but if I look at that A cosine omega t, that guy there is the same as that guy there. So I go, oh, okay, my acceleration is equal to minus omega squared x, and that's where that comes from. Just another little thing. Let's have a look. Okay, spring and block system oscillates with simple harmonic motion. The block is moved 5 meters from its equilibrium position. The block is released and the system has an angular frequency of 2 radians per second. What is the velocity of the block 1.7 seconds after the block is released? I can't do that problem just now because it's just words to me. I can't tell you what to do with that. I got to figure it out. So what I do is I go, okay, we have a spring and block system. So I got to draw it. So there's my spring. I'm not a great artist. It's good enough. And it oscillates with simple harmonic motion. So I know that kind of like there's my equilibrium position. I've stretched it to the side and I'll get simple harmonic motion. Okay. The block is moved 5 meters from equilibrium. It should say 5 meters in a positive direction or 5 meters to the right to be clear. But it just says 5 meters from the equilibrium position. The block is released. It should say when t equals 0. The system has an angular frequency. Okay, so omega, I've got to know what the symbol is, equals 2 radians per second. And what is the velocity? So I want my velocity. And the time is, well, if I started at 0, I'm now at 1.7 seconds. If I started at 5, I'd be at 6.7 seconds. I got to give you, and I said here, after the block is released. So I'm telling you how long it is since the block was released. Sorry, well, anyway. Okay. So I got to do my thinking, and what I do is I go, oh, let's have a look. I know that x is equal to a cosine omega t. So v is equal to, what is it? Big A. Big A omega sine omega t. Did I do that right? And what would the A be? What would it be? Minus a omega squared cosine omega t. Why do I write them down? I write them down because the more you write them down, the more you're going to remember them. I want the velocity. So the one I'm picking is v equals minus a omega sine omega t. I didn't write down that omega t, sorry. Okay. So it's minus a omega sine omega t. I got an omega, I've got a v, I want a v, I got a t. Oh, what about my a? What is my a? Yeah, it doesn't say a. It says the block is moved 5 meters from its equilibrium position. So I told you a, I just didn't use the word. And that's what my questions are kind of like. I'm not going to say amplitude is this and velocity is that. I'm going to paint a picture in words, and then you've got to extract from there what the things are. And so I say, well, okay, now let's put the numbers in, so I go minus 5. I've got to be in SI units. Omega should be in radians per second, and it's 2 sine 2 times 1.7. So V is equal to minus 10 sine 2.8, no, 3.4. So I do that. I get my handy dandy calculator. And what's the first thing I do when I'm doing anything with trig on this calculator? Yeah, I check the mode. Now, what should I be in here? I'm so sorry. My wife is having a conversation. Sorry. She doesn't. So what should we be in? Degrees or radians? Radians. How do you know? There's context. There's context, but you're dealing with stuff and it's radians and radians and radians. I suppose I could give you stuff in degrees, and I can talk about that later. But, from context, omega is in radians per second, so you want to be in radians. So I click on here. These calculators are great because they actually tell you what you're in. And I'm actually in degrees. So what I do is I go DRG, and I click across by 1, and I go enter, and now I'm in radians, and it says RAD on the frame. So you're pretty set on that. And then I want, let's have a look, 10, enter, times sine, it's going to be 3.4, 3.4, close bracket, enter, and I am getting 2.5, and I go, there's a minus sign in front of it. So hopefully I did that right. V is equal to minus 2.5. So V is equal to plus 2.5 meters per second. And there's my answer. I got 2.55. I rounded it a bit more this time. It's 2.55. In degrees or radians? Yeah, cool. So there it is. There's a pitfall. Am I in degrees or radians? That will catch some people out. But there's the approach, and for me, that's the approach I always do. I read it, I draw a diagram, I list my parameters, especially if I'm uncomfortable. If it's f equals ma, I don't list my parameters. But if it's like more complicated, I need to jog my memory about the equation, I find listing the parameters really helps. And then I get my equation, and then I put my math in. And from a testing point of view, what do? I look here, I pull out all the papers that have the right numerical value, and I look through those first, and I go, yeah, I'm checking the work, but they're the ones that are easy to grade. And then I pull out all the papers that are just like nothing's written down, and it's like it's a mess, and they get pulled out and they get graded. And then it's the ones where it's kind of like somewhat in between, where they started off okay and there's elements there, and I'm trying to sort out, am I going to give partial credit, and if so, how much? And what I look for in that is, the first thing I look for is there an equation on the page? And if there's not an equation on the page, I'm not very sympathetic, because we've got to learn to write down equations. And if the equation on the page is wrong, then I'm sorry, but it's the wrong equation, so I'm kind of done. If the equation's right, then for me it's like, now what went wrong? So then I like to see the numbers put in, because I can see, oh yeah, you know what they did? They got that -5 here, and they got the -2 on the thing, and they forgot about that minus. But they wrote it down correctly, so it's not such a big deal. Or they give me that, and they give me that, and that's got a negative sign in front. And I'm going, what? Then that's hard for me to sort out. So the more information you give me, the more I can mitigate, not guaranteed, but the more chance I can mitigate and recognize that your mistake was a small one rather than a big one. No equation, I have no idea what you're doing. It's like, I can spend time and try and figure it out, but I'm still guessing in the end. because you're giving me the math and the math is wrong, otherwise you'd have the right answer. So it really helps. You're not, the first people leave my tests after about 40 minutes typically, and there's always somebody who's there to the end, and I would be that person. I hated leaving tests early because I'd hated walking out and finding out, oh man, it was 27. So I would stay to the bitter end. But it's not that no one can finish on time, so you can slow down. The more you write, in the end, I think the faster you go. But that's just my opinion. Questions? Okay. Cool. There we are going. So let's do a bit more. Now we're playing. We say, well, okay. So that last bit was very important. Now we're playing. We're going to say, what's the natural frequency of this? Well, we figured out before that our acceleration is equal to minus the spring constant over the mass times my position. I'm sorry this didn't print out so well. That sometimes happens when I go to from a Word to a PDF and then from a PDF to a thing. So just bear with me on that. And I know that A is equal to minus omega squared x. We got that one from the last little bit. So then we have so I'll come back. I'm going to have to do it, aren't I? I'm just going to have to do it old school way. So A is equal to minus K over M times X. And I know that A is equal to minus omega squared X. Let's have a look. I can say that my omega squared... And can I do it the old school way? I'm getting... Is that it? K over M equals omega squared. K over M is equal to omega squared. Yes, what we do is we say, let the two A's equal each other. So I'm going to get minus omega squared X is equal to minus K over mx, and the x's cancel. So I get omega squared is equal to K over M. And so omega equals the square root of K over M. So omega is equal to the square root of K over M. That's what I'm doing. Now, omega is the frequency. You make the spring stiffer. I expect a higher frequency, so K should be on top. Mass is inertia. Put more mass on the mass. I expect it to be more sluggish. So lower frequency. So I expect mass to be on the bottom. So this makes sense. The square root sign would not be obvious to me intuitively. It's something that it's a bit surprising, but I might remember it. But I couldn't just figure it out just by looking at it and saying, well, that makes sense. I don't know why. I don't see why it should be a square root, but it is mathematically. And then I can play some games, and I can say, well, hold on. If t, the period, equals the number of radians in a circle divided by the angular frequency in radians per second, then I can say, well, hold on then. T is equal to 2 pi times omega, and omega, divided by omega, and omega is equal to, well, it would be square root of K over M. I'm dividing by that, so I'm going to get me square root of M over K. So there's a little bit of a rub here. This is K over M for the frequency, and this is M over K for the period. And that does make sense because the period is the inverse of the frequency. But in my memory, that can get to a stage where I thought, which way around is it for this one? So I remember one, and I'll figure out the other. So many of you may have learned that T is equal to 2 pi root L over G, yeah, for a pendulum. Well, that was the first one I was introduced to. So for me, I can always infer this from it. But if I was to learn one, I would learn that. And I can always figure out this from that. If you know one, you can figure out the other. Yeah? Or just get comfortable with them both. We just worked out the period of an oscillator, mathematically. We worked out the period of the oscillator. It depends upon 2 pi times the square root of the mass. If the mass is bigger, the period's longer, divided by the spring constant. And the spring constant is the stiffness of the spring. So that was kind of nice. A spring and block system oscillates with simple harmonic motion. obstacles with simple harmonic motion. Spring has a spring constant of that, the block has a mass of that, the block is displaced 3 meters from equilibrium. What is the period? Can you have a go at that for me, please? Can you just have a go and see what answer you get? I'm going to pause this. So let's have a look at this. So I have my spring and block system. So I'm going to do my table with my spring. Here's my block. It's 32 kilograms. Here's my equilibrium position. And this thing oscillates like that. And I know that this is going to be 3 meters to the side. And let's work through it. I know that my K is equal to 8 newtons per meter. So I've got to know what the symbol is for K. I'm not going to give you K is equal to 8 newtons per meter. I'm going to just tell you it's the spring constant. And then you know the mass is equal to 32 kilograms. And then we know that the amplitude is equal to 3 meters. And what do I want to find? Don't forget to write down what you want to find, or else you might be there all day and not being able to solve it. And what I want to find is, what is the period? So period is big T. Memory. What could it be? Oh yeah, T is equal to 2 pi square root. Which way around is it? As the mass gets bigger, the period gets longer. So it's going to be that. So then I say, well, T is equal to 2 pi times the square root of 32 over 8, which equals 2 pi times the square root of 3/8 of 24, 4/8 of 32. So T is going to equal 4 pi. I can leave pi in for today. In a test, I'd actually want you to work it out, because some people do and some people don't, and some people make a slip with it and all that. So there's many things I like you to leave in. Big G, I would have had you leave in Physics 1. And we're going to use mu naught and epsilon naught. You just leave those in. But, you know, other things I like you to work out. But for today, we can just leave it as 4 pi. Now, it's not complete yet. I've got a big problem, which is there's no units. Sometimes people, they have like a mental check. And if they put down a pi or a mu naught or a k or an m, if they leave that in the answer, it's almost like they've put a letter down so the units are taken care of. It's like the little alarm bell doesn't go off, and yet there's no unit. So I see sometimes with numerical answers, they'll put down unit. Then you get this thing where there's a letter inside it and they don't put down any units. It's like you've got to remember to put down the units. If you don't put down the units, it's like, oh, you don't care about units? Okay. I'll give you 5 bananas for this question. It's not points, don't count towards your grade, but I gave you something. You know, if units don't count, then what I give you doesn't count. Units are just as important as the number. We need them both. So always be on that one. Oh, yes, more playing. So let's think about energy. This thing must have energy inside it. I did work when I moved that spring to one side, so it must have some energy inside it. And at any instant, we know from Physics 1, mechanical energy is going to be constant in the absence of friction. Mechanical energy is made up of, in this case, it would be, well, now, we're going to talk about a horizontal spring. It's going to have spring potential, and it's going to have kinetic. We're not going to have potential, gravitational potential, because we're not going up and down. We're going to just think about the simple case. So then we say, okay, well, we can derive the kinetic energy, we can derive the spring potential energy, and we can just see how they compare. So we say, well, let's start with kinetic energy. Kinetic energy equals a half mv squared. Let's have a look. Oh, I know what V is. V equals minus A omega sine omega t. So my kinetic energy equals a half m minus A omega sine omega t all squared. And I can multiply that out, and I get the kinetic energy equals 1/2, and then m, and then omega squared, and then A squared sine squared omega t. And I can say, well, let's think about it. At this point here, I have all kinetic energy and no spring potential energy because I'm at the equilibrium position. So I could say, well, at that point there, my energy, my total energy, equals my kinetic energy plus my spring potential, and because I'm at the middle position, my spring potential is 0 and my kinetic energy is maximum. How do I get that to be a maximum? Oh, I just make it equal to 1. Sine cannot be more than 1. Sine squared cannot be more than 1. So you want to know your maximum value, just make your sine bit equal to 1. So then that means that this maximum value of my mechanical energy is equal to a half m omega squared a squared. Let's stop for a minute. Depends on your mass. Depends on the frequency squared. That's kind of like a little bit surprising. Double the frequency, 4 times the energy. All other things constant. And it depends upon the amplitude squared. Double the amplitude, 4 times the energy. It might not change the period, but it changes the amount of energy. You did much more work getting the thing in. Think about the line for a spring. The force is not constant for a spring. If you look at force versus position, it looks like that. If I double my amplitude, if I double my position, I've got the work is the area under the curve, so I have that bit versus all of that bit. So doubling your doubling your displacement does not double the work done. Okay, it's more than double the work done. So that kind of makes sense. Again, I might not guess the squares, but it kind of makes sense when I see them. If I look over here and say my spring potential equals a half kx squared, I know the expression for x is half a cos omega t. Substitute in, I get this guy here. And remember, I've got to remember that my k is equal to m omega squared. So then I say, well, u is equal to a half m omega squared a squared cosine squared omega t. Oh, man. Okay, that looks, one's a sine, one's a cos. Okay. And then we go, okay, add those two guys together. At the extreme is that for there. At the extreme, you have all spring potential, you have no kinetic energy, and you end up with the same answer for the maximum, for the total mechanical energy is the same. Cool. Okay. Same answer. At any instant in time, what I have, if I have more kinetic, I would have less potential, because one's going to be modified by a sine squared of the angle, and the other one's going to be modified by the cosine squared of the angle. And what is it? Sine squared plus cosine squared equals 1? Yeah, so it makes sense. It's playing. It's playing with, we know some equations, let's play with them and see what we can figure out. We just figured out the kinetic energy, the spring potential at any instant for our spring in there. We're using physics 1, and we're just playing and seeing what we can figure out from it. Spring and block system oscillates with simple harmonic motion. 4 kilogram block is displaced. So I'll do this one. So we have, let's have a look. Oh, I'm sorry, wrong diagram. It's no big deal. Sometimes eraser. Go back here. Pen. So string and block system. Boom, 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 boom. Oscillates with simple harmonic motion. There's my equilibrium position. 4 kilogram block. 4 kilogram block. Displaced 2 meters. 2 meters. Time t equals 0. I'm getting better, aren't I? I'm defining things better in my question. The system has an angular frequency, so omega is equal to 5 radians per second. What is the instantaneous kinetic energy? Here's what my kinetic energy equals. My time was equal to 1.3 seconds after the block was released. So, okay. What else do I know? I know my A is equal to 2 meters. I know my M is equal to 4 kilograms. So I put those together and I put my scratching head on and I said K is equal to 1/2. What was it? It was A squared, omega squared. And then for the kinetic energy, because we started by moving it to the right and letting it go, it was a cosine relationship. So I think this was cosine squared omega t. Am I right in my recollection of that equation?
For kinetic?
For kinetic, yeah.
No, it's
Sine, oh, ratsaroni. But everything else is okay.
It's a,
Yeah, everything else is okay. Yeah, I got the sine and the cosine backwards.
yeah, there's a mass of the mass after the 1/2.
Oh, man. Okay, not so good then. Guess what my homework is tonight? So then we go K is equal to a half, and I have my mass, and my mass is 4, and I have my A, and my A is 2 squared, and I have my omega, or my omega is 5 squared, and I have my sine of, and this is going to be omega, which is 5 times t, which is 1.3. So I say it's a k is equal to 1/2, 4, 4, 25 sine 5, 5 3s are 15, 6.5 I think that is. So k is equal to 4 4s are 16, half of 16 is 8. 8 times 25 is 200 sine 6.5. So k is equal to, I get my calculator, check I'm in radians, 200, oh I'm sorry, it's sine squared, isn't it? So I need to do sine squared, I need to do sine squared, I need to do sine squared. So I've got to be a little bit careful here. What I do is I go sine 6.5, and then I got to square that. That's what that means. It's not sine of the angle squared, it's sine squared. And then I got to multiply by 200. So that equals 9.26. Joules. It's positive. Happy days. Okay. Not so bad. Now, going through these equations so far. That's fair game. But you can derive it from those two. So either learn it or learn those two, yeah? These are really important. Much more often, these will be on a test, you know. I get about 3 questions per chapter. Okay. Quite important. I think that's quite important. It comes up a lot. Not so important. I care about that. That's why it's in yellow. I care about that. I care a lot about that. But that's what we had up here. It's just a different version of that. What I'd be inclined to do on these, actually, is I might give you that equation. And I say, given this equation, plot me a graph of. So then, I give you the equation, but you've got to be able to interpret and interrogate the equation. So I wouldn't expect you to commit that to memory. I think I should know it, but I wouldn't expect you to commit that to memory. But I might give you it, and if you don't know what the letters stand for, then that's just tough luck, you know. So you can't just ignore it and say, oh, it's never going to come up. I might give you it, and then say, well, how does this relationship go? So, yeah.
It's the energy of the system.
Yeah, that's the energy of the system, yeah. Maximum energy, the mechanical energy. How do we deal with this business about not having this thing going to the right and letting it go? How do we, supposing I just don't want to let it go when the clock equals 0? It seems like it's a horrendous problem. The timing will all be out, and what does that do to your map? And it turns out it's remarkably straightforward. So this is a graph showing what happens when everything's well behaved. So you move this object to the right and you let it go when time equals 0. And then time passed and it did what it does. It's a cosine relationship. Okay? This is where you actually effectively either moved it to the wrong position and threw it a little bit, or you let it go too soon. And so what you're going to do there, and what you do there is you recognize that I can express that mistake in time by an angle. And so I say that's just an angular difference, and I add it on. So it's called a phase constant or a phase difference, and it's expressed in radians. If I was a half a period out, then my phase angle would be half of 2 pi radians, because it's half a wavelength. A wavelength is 2 pi radians. One circle is 2 pi radians. A wavelength is 2 pi radians. Half a wavelength is 1 pi radians. So that phase constant would be pi. If it was a quarter of a wavelength out, that would be pi over 2. If it was 1/17 of a wavelength out, it would be 2 pi over 17. It's not bad. It makes life, what could be an awful situation, it makes it very nice. Some books put that in from the very beginning, kind of get used to it, and my sense is, oh man, let's just deal with what we have to deal with, and then we'll go from there. Other books decide to work in hertz. They say students are not comfortable with radians per second, let's deal with hertz. And the relationship is, again, omega equals 2 pi f. So what they do is, every time you see an omega, you put down 2 pi f. So we have x is equal to a cosine 2 pi f times t. And this would be, and so on. Every time you see the omega, you put down 2 pi f. And I just found, that's the way I was taught. You ended up with these really long expressions, and it looks daunting when you get it. And I just made the choice that I think that it's good for you to get comfortable with omegas, and then we can have a more complicated equation if we work with hertz. That's an equation that if you woke me up from the deepest sleep, I would know that relationship. It's just good. So draw a line, bit of a change now. We're going to do stuff that's a bit more practical. Supposing we have damping. Well, there's always damping, but supposing we have significant damping, what happens? Well, energy's lost, isn't it? There's friction in the system, so energy is lost to heat. So as time passes, we lose energy. And what we found was, let's go back a bit. What we found was the energy in the system was equal to a half Ka squared. As the energy decreases, your half doesn't change, it's a constant. And your K doesn't change because it's the spring. The only thing that can change is the amplitude. And so as the energy decreases, so the amplitude decreases. And we saw that. Yeah? As time passes, the pendulum stops swinging as much and the thing stops oscillating as much. Okay, so that kind of makes sense. So I expect my amplitude to decrease. Is the frequency going to stay the same or change? That's not obvious to me, at least. That's not obvious to me. So what they do is they try and characterize the friction. It turns out that friction is linearly dependent on velocity. If you double your velocity, you double your frictional force. Triple your velocity, triple your frictional force. So we say, well, force is equal to, and if my velocity is in that direction, my frictional force is in that direction, so there's a negative sign in there. So it's minus some constant times B. B for air would be a small number, B for syrup would be a big number. Or frictional force. So B has got some physical relevance called the coefficient of friction, and you can look it up in a book. You can find it. V is the velocity in meters per second for the mass. So then we start saying, well, hold on then. We have the sum of the forces equals MA. And let's have a look. I know also that the force is equal to minus Kx. Well, there's two forces on this, isn't there? there's the restoring force of the spring. Let's say that I'm like this, and let's say I've come out here and I'm boom, but I'm in the bottom of a syrup tank. So there's the restoring force of the spring, and then there's the frictional force. Let's call it F drag, FD force, and they're in. So I've got to take both of those into account. The restoring force of the spring is given by that guy, and the frictional force or the drag force is given by that guy. So you start putting these together and you get that. You recognize that velocity is dx by dt, and you recognize that A is d2x by dt squared. So we got a classic differential equation. We got d2x by dt squared, dx by dt, and x in there. So it's a classic differential equation. And most people don't do differential equations before this class. At USF for sure, they've not done differential equations before this class. So the book says you might not have done this. Here's the answer, okay? And the answer is that the position is equal to A amplitude e to the minus b over 2m times t cosine omega t, and your frequency, which was the square root of k over m, is modified. Your frequency is modified. So not only does the amplitude fall off, but the frequency does change. Okay? And you can figure out even what the new frequency is. If that's the old frequency, this is a new frequency. And what do I want you to know about that? I want you to know that the amplitude falls off and the frequency does change. That's all I want you to know conceptually. This is great, and if you've done the differential equations, if you want to have a go at it, have a go at it. I've not done the differential equations on that in years. But all you need to know is conceptual stuff out of this, because you don't need differential equations for the class. And then the other thing I want you to know is this, and that is, if you have a mechanical system, it's got a natural frequency, and you might want to damp any oscillations using damping, and you can damp too little. The way you do it is you have a chamber and you have a piston, and as this thing oscillates, it messes with what's in the piston. So you put air in and you get a certain amount of damping. If that's not good enough, you put water in. Oh, water's incompressible. You put some other thing in, and you change the system. So you can change the degree of damping. If you have no damping, you're going to get basically, if you have a bit of damping, but it's not enough to efficiently stop the oscillation, you'll get what's called underdamping, where, yeah, there's a fall off in the amplitude, but it's not, it does overshoot. You do overshoot. You go down here. And so that is underdamping. You didn't damp enough to be the most efficient getting rid of oscillations. Then there's a critical damping. You made it a bit more damping-like, and you more slowly approached the equilibrium position, but you did not overshoot. So it's the amount of damping you need so that you don't overshoot, but you get there as quickly as you can. And then there's overdamping, where, yeah, you don't overshoot, but you take way too long to get there. So this would be a viscous medium. This would be a not so viscous medium. This is not viscous enough. I'd like you to know those terms and those diagrams. Okay? So I'd like you in this section to know, yeah, the oscillation decreases as you oscillate inside a damping material, damping medium, because you're losing energy, and also the frequency does change. And also the frequency does change when you're damping. And then secondly, I'd like you to be able, if I said to me, draw me a graph of underdamping, you could draw that diagram. Or if I showed you that diagram and said, which is this? You could tell me it's underdamping. Or you could tell me what the axes are for underdamping. Just conceptual stuff on that. And I'll be happy on that. Okay? last little thing on this. Every material, every mechanical system, every object, for example, has a natural frequency, and you can hear it. Put energy in, and the thing oscillates with a natural frequency. I do put the same amount of energy into a different system, different natural frequency, same amount of energy, but different frequency because of a different mechanical system, different mass, different Ks. Complicated situation. This has got different lengths. It's a really complicated situation, but you can hear the effect. If I take a oscillator and I recognize it as a natural frequency, and I can see it's got a natural frequency like that, and I drive it at the wrong frequency. I don't increase the oscillation. I just mess it about. Yeah? If I randomly I might even take energy out. I don't get an increase in oscillation. But if I look at my natural frequency and I apply a driving frequency, which is the same frequency, I add more and more energy. And so I get more and more energy in the spring, and so I get bigger and bigger amplitudes. That's resonance. Okay? That's resonance. Resonance is when the driving frequency, me, is matched to the natural frequency of the object. And you store more and more energy in, and so you get amazing things like, bridges fall down when soldiers march over instead. In the Boy Scouts, we're always taught break step when you're walking over a bridge. It's not going to happen, but, it's good teaching. So you've seen that thing where some people can sing and they can cause a wine glass to break. Sometimes you get the wind around buildings causes a kind of woo. And if that frequency, that woo, is the same as the natural frequency of the panes of glass can oscillate more and more, and they fall out. It's amazing things happen because when you're at resonance, you put more and more energy into the system. And at some point, the system cannot maintain that, cannot contain that amount of energy, and so some breakage takes place. I'd like you to know that resonance is when your driving frequency is the same as the natural frequency. That's all I need to know from that as well. Okay? And then we're done. Good. So let's